Hello community, so great that you are back. Today we have a crazy new paper. It is about a new visual reality. So you know that our autoregressive LLMs now serialize the data in a rigid raster, imposing here an inductive bias that fracture here our spatial causality in the vision domain. Now, the beauty is now, can we get rid of this? And can we have now a much more flexible way, an API for interacting with the non-linguistic portions of course, world models. This means motor, memory components, everything that is connected here to the visual elements. In language, it is easy, with a GPT. A single model with a unified prompting interface excels both at the controllability and the queryability of the scene. But in vision, we do not have this. We have different interfaces, we have different separate models. We have models for generative tasks and we have models for discriminative tasks like segmentation. But now today we have a paper where we make the next step in vision. Because there's this beautiful new idea of a probabilistic structure integration. So this is now, I will show you, hopefully I can explain this to you, a generic process for building rich, controllable visual world models. With the right interface for an interactivity with the human user, even when you start here from a low-level, non-linguistic input data. And yes, we only will have here video frames. Now, what is the basic of the new paper? We break down the complete world data as represented in a video into a set of local variables. And then we have a new system to learn to predict the conditional probability distribution of each such variable with the flexibility to condition on any subset of those variables in our video frames. So if you want a little bit more on the mathematical side, in other words, we learn a probabilistic graphical model, a PGM, on the variables characterizing here this particular world model and this particular scene in our video sequence. If you're not really familiar, probabilistic graphical model is a statistical framework that represents the joint probability distribution over a set of random variables using a typical graph structure where you know we have nodes and edges, where the node correspond to the variables that we're interested in, and the edges simply denote the conditional dependencies between them. Now, of course, it is a little bit more interesting because the model leverages here the graph theory to an extent to encode the conditional independence relationship among the variables, simplifying thereby the representation of complex probability distribution by factorizing them into local conditional probabilities. And this is what we need for a simplified mathematical procedure. So therefore, in this PGM, the joint distribution can be expressed as a product of conditional distribution. So similar what we do with mathematical spaces based on the graph structure. Parent models, parent nodes, yes, categorized into the direct Bayesian network and the undirected Markov random field types. And you know all of this because we talked about what is at the heart of any AI system. Why does AI run on uncertainty? So let's have a look now. Let's go a little bit deeper. Let's go a little bit on the technological side, unlock the reality, the visual reality. Now we do have a predictor psi. Psi begins with a probabilistic graph model predicting the likelihood of observing any subset of any pixel patches at a specific location within a video frame, time frame, conditioned on the observations of 0 or more other such patches elsewhere. So what this predictor does, it models now the conditional distribution over local spatiotemporal variables, representing them as pointer-structured patches of RGB values. And yes, of course, it's not a fixed tensor structure, and I will explain why we deviate from a tensor structure a little bit later. Pointer are so much more flexible, enabling thereby flexible interference pathways akin to a large language model prompting, but tailored now to the visual domains. So this is now the beauty of the idea. They say, hey, listen, we do not need a vision language model. We do not need a vision language action model where the complete intelligence is in the linguistic encoding and the reasoning and the understanding of the world is only in the linguistic part, but not in the visual part. And now they say here from Stanford, you know what? Forget about linguistic. Nature doesn't know what language you speak. But if you see a ball bouncing on the floor and you make a video and you take a video of this, then immediately this is encoded. So just looking at nature, you kind of find a representation of the laws of nature, and therefore we work now completely in the visual domain. And of course, everything is with probability distribution and a little bit higher mathematics. So this PGM that we're working now is approximated, guess what, by a neural predictor psi, designed to model the joint probability distribution over the local spatiotemporal variables. Specifically, since we look at video frames, tokenized RGB patches defined by their pointer location, IG and the time t, and their associated values in a vocabulary V. Of course, because in the next step I will show you, we will build new elements here in the visual domain, and those elements we will assign a new vocabulary term, like a new technical term that you have in a technical paper, and this will define a new object, and therefore we can then calculate and visualize those objects with different flow states. So what a beautiful idea by Stanford. So these patches that we have now, let's say a 16 times 16 pixel patch, represent now random variables of our video frame, and the edges in the PGM encode here the conditional dependencies between them. Now imagine for a video frame, my goodness, what a computational capacity you have to empower now, because what you want, this is learned through a random access autoregressive sequence model. So means our GPT model, for example, we don't have to build here some crazy vision transformers, but we go with an autoregressive model known now as a local random access sequence modeling, or LRAS. If you are not familiar, this is the paper, September 15, 2025, Stanford NeuroAI Lab, World Modeling with Probabilistic Structure Integration with the archive link. An absolute fascinating paper. The first 5 minutes I thought, I have no idea what they are talking about. You really have to take your time. You have to sit down. You have to read this. But it is fascinating. So let's talk about this probabilistic predictor, psi. Psi models now the complete world model of the AI as a probabilistic graph model, as I told you, where each local variable, as we just discussed, is a small spatiotemporal patch. As I told you, maybe 16 times 16 pixels square, go to 32 times 32 in a video frame, tokenized now into discrete values. And this is now real similar what we have here, the tokenization here in the linguistic part, so the words in the language or the sub-word token, whatever you choose. So what is now important, we don't go with a fixed tensor structure, but with pointer structured patches. So each patch has here a pointer, the location IGT, for the row, the column, the time, position, location, whatever, and the current RGB values or whatever you have, black and white values, whatever you work with. Great. Now, what is the job of this predictor psi? It is now to predict, guess what? The conditional distributions. So given some observed patches, some conditional x, what is the probability distribution here over all possible values v at an unobserved pointer p? And now Stanford gives here as a very simple equation here, where d is here the data distribution, v is given here by a given vocabulary that we can extend now, given that we have action modules, but more about this in a minute. Yeah, I told you about psi uses here the local random access sequence modeling. So what it does, this treats data as sequences. Remember, I told you we want to stay with our GPT systems. We don't want to build new heads. We don't want to explode here the complexity of the architecture of new AI models. We want to go along with the models that we know, autoregressive system. So therefore, we need a particular sequence. But now this sequence is not a left to right or whatever sequence, but this becomes now a random sequence, which is absolutely fascinating. Random access, this means we condition on any subset without fixed order, and this will help us a lot because given now a particular data structure as a sequence, we have at first the pointer tokens and precede here the content tokens. Pointer tokens, value tokens, pointer token, value token, and so on. Now, the next key component we have to understand is here a local quanticizer for the visual domain. Now, interestingly, we have to go now with a hierarchical local quantizer. And guess what? First the lower resolution base code, and then the residual details. No? And here, what a coincidence, they use here for the higher resolution a wavelet structure. Why? Because we want to preserve the locality of our mathematical operations. No? We want that this mathematical operation has here a fixed point in locality. So all the prediction that we will do with psi respect here the spatial temporal neighbors, reducing here the complexity. So therefore, I hope you have seen my video on wavelet operator theory, where I told you if we go beyond GPT-5 and we go an operator-based machine intelligence, this will be the next step. This is about 2-3 weeks ago, and guess what? Today, Stanford tells us we use wavelet MLPs. No problem. Everything is explained in this video. Great. Of course, we use entropy, our beautiful uncertainty measure here, to guide here high entropy patches here with many possibilities, because we will resolve those first, reducing here the overall variability. So therefore, if you want, psi predicts here the video futures from partial frame. But you know, this is not enough. It lacks here a deeper insight into the probability distribution of other operators like flow or motion, translation, rotation, and so on. So what we have? But we have a very powerful psi model. Now, it's a learned probabilistic graphical model over the patch variables in which any observation can condition any prediction. There's no limitation. If you watch all YouTube videos of all bouncing balls on this planet, on all surfaces, on all colors, on all textures, on all materials, on all internal air pressure of this ball, you will understand, you can predict after having watched, 1 million videos of bouncing balls. Now you can predict, if I give you one video frame, the future. At least the next 2, 3, 4 frames. We're going to talk about it in this video. So, learning here a full probabilistic model of this kind might sound like a challenging problem, but the key technical advantage here is to formulate a psi model so that it can be scalability learned from raw video data. So it's just about some trillions of video frames. Hey, come on. You are a global corporation, no? As I told you, we want to stay with our transformer architecture, our autoregressive transformer architecture. We don't want to build another complex architecture for this damn thing. So let's stay with what we have. So therefore, we are bound more or less by a particular sequence structure. No? So we learned that stepwise conditional distribution and many random orderings of the same sparse individual data have two main advantages. At first, they are extreme data efficient and enabling us to repurpose here, if you want, the high scalability of modern LLM code infrastructure, while avoiding to build additional heads into our layer structure of the transformer, task-specific head or whatever specific heads, or architectural forks. We just can go with the models that we are familiar with since we have a sequence. Okay, second part. Now it gets a little bit more into detail because now we want to the AI wants to uncover the hidden structure it sees, it detects here in a video frame. So now we come to lower dimensional patterns in our video frames, in the sequence of video frames, like motion, like the ball bouncing, or object groups. Maybe in the background there are two people talking or whatever, but what are the objects? What are objects group? The eye has to understand here the content of this video frame. So therefore, structure extraction is the main topic. Structure extraction isolates 0 shots or no labels via a causal inference on the PGM. Sounds crazy, is beautiful, and they give us here 3 examples here of an optical flow, of an object segment, and of the depth. Remember, those are the classical things that we have built. If you look back here on the videos on my channel, particular models, neural network that were only designed for optical flow detection, object segmentation, or depth structures. And they do this via tracer counterfactuals, motion hypotheticals, and viewpoint hypotheticals. Great. So, summary. Just come back. What are we talking about? So we do have 3-step process, no? We have a ground truth, we have a video frame, and then our psi predicts now the future. Probabilistic prediction, what is going to happen in the next 2 video frames. Then, causal inference, we have now the structure extraction This is what we are talking now. If we see here a bouncing ball here, maybe it's bouncing here on this, we want to understand the flow operate on a mathematical framework in a mathematical space, and we will approximate this here in a particular way. We have to segmentation. What are, I don't know, what are pumpkins, what are nuts, what are lemons, what are whatever. So the segments here of this, and then the depth information here. What is in front of, what is background, what is here in the medium. Great. And this is now rather easy. But if we have this information here on a video segment of 4 video frames, we can now, AI can now determine the flow token, the segments and the depth and the variation of the depth and so on, and build now new objects. And then we feed those objects back. So we integrate those objects, these structures back into the learning process of Psi. And now we have, we can combine them in various ways. For example, here a camel, you understand here the flow dynamics of segmentation. That is here the camel, if you want, in a little bit abstract way. We have the depth information, everything. We have the RGB information. Now we can build it here and go to higher complexity objects here that we integrate now, and then we can calculate with these higher complexity objects. So we start really from the ground up. We don't have to have any linguistic pre-training here of the model, that the language model explains the vision model here, anything at all. We are only here purely in the vision domain. There's no linguistic structure overlapping here into vision. So what the authors do, they say we propose a new system for constructing a self-improving world model. Wow. For the vision domain, wow, of a 3-step cycle. 1, 2, 3. So at first, a probabilistic predictor. This is our Psi that was trained here on trillions and trillions of video frames of raw input visual data, RGB pixels. Then the model is prompted here to produce counterfactual generations, and here all these flow segments and so on. Great. So we have now the, if you want, finer grained dynamic structure, like an optical flow, like the depth information or the segmentation of the objects in the image. And then, as I told you, those structures are now detected, become now a new token structure. So we add this technical term, this new token, to our vocabulary of our AI system. And now we can calculate with this, and we know it has certain depth conditions, and we can calculate with this. Yeah, and we have a continual training exercise to improve the prediction, and we can expand the capabilities. It will learn more and more about particular car type, about particular camels, about particular fruits, about particular vegetables. So it will build a world model. It will understand, after have seen trillions and trillions of video frames, what the world is. Hopefully it's not AI generated, because then we do have a major problem. So just to tell you, this is not just happening today. Here is, for example, the original paper, the LRAS, the Local Random Access Sequence Modeling. This is a work that was published here by Stanford University in cooperation with OpenAI already in April, beginning of April this year. So you see, those models are years and months in the making, and now they all come together. Now we have this great synthesis that is going to happen. But if you want to see here the architecture now in the current implementation of the paper that we're going to talk today, this LRAS architecture here you have your ABCD. Yeah, ABC. So what we start with, we have our Psi model with a local random access sequence architecture. You go sequential decoding, parallel decoding. We have our pointer tokens that enable now the random access. Remember, we are not here in a linear structure, right, left, or left, right. We have our patches, we have the pointers, and we have a learned local quantizer. Maybe we should talk a little bit about this. Okay, great. I told you about the encoding, how we code this, not with a fixed tensor size. This would be inappropriate because we have so much more powerful pointers in this. So, core insight the author tells us is that this problem can be solved by reformulating or reframing Psi as a sequence prediction problem in which the pointer values are simply woven into this particular sequence with one pointer p token before each value token, as I showed you. And therefore, we have our beautiful sequence for our beautiful autoregressive transform architecture. We don't have to add any head or anything at all to the architecture. Now, the learned local quantizer, you are familiar with this here. 2 years ago, we did a lot of videos on autoencoder and denoising and convolutional variational autoencoder and vector quantized variational autoencoder. This is the way we normally do this. You are familiar with this. You have seen my videos. Here now we go one step further. We go with a hierarchical local quantizer. So what it is, it's a classical convolutional autoencoder whose receptive field never crosses the patch boundaries during the encoding. So this is important because you don't want this. You don't want this pollution if you want. Huh? Each patch is encoded into a sequence of 4 codes. First code of each patch reconstructs a low resolution preview, while the remaining code adds here all the fine details that are necessary for a better resolution. So training and training infrastructure. Stanford tells us we train here an 80 million parameter HLQ on a combination of ImageNet and open images and whatever. We train a 7 billion parameter PsyModel on a dataset of 3 million RGB video clips, consisting of about 1.4 trillion video tokens that they generate. And this is surprising. If they just go for a causal sequence of 2 to 4 video frames, so 4 seconds of video, it's okay, that's a little bit strange. They just need 64 H100 GPUs here. So this is done with a low computer infrastructure requirement. Yeah? Because if you do this on all YouTube videos, my goodness, you have to be Google, I suppose. Great. Infrastructure. Yeah. I told you those 3 elements that they present in the paper. Let's have a look at this optical flow. So what is the flow operator here in the visual domain? How they do this, how they extract this optical flow is here the motion vector field. So how the pixel of this bouncing ball, for example, move now video frame to video frame. Extract by intervening here, add traces. So you have little perturbations to patches in the first frame. Then you predict the next frame distribution. You compare to the baseline, to the factual, via a Kullback-Leibler divergence comparison. And you have the distance between those probability distribution, and we are here on familiar turf. Great. This isolates here the causal effect of appearance on particular positions here in the video frame. You'll have sharper flow maps outperforming here the supervised methodologies. Second, segmentation. Segmentation is now you segment group pixels with a common fate. Let's say you have a video sequence of 4 video frames. What moves together? So the head moves together with the upper part of the body. These are now, if you want, segments that belong together. Cluster the covariances. If you want to go a little bit more into the mathematics here, correlated changes is here mathematical methodology. Have a look at the paper, they explain it here beautifully. And third here, the depth information here of any image or video frame is important. The depth maps the distances, no? Intervene by prompting novel viewpoints. You shift the camera, you compute a parallax, average over distributions for reliability. Great. So, a little bit of time, short summary. These emerge zero shot because Psy's PGM captures here covariances. This is so important to understand here. Ne? On all the extracted structures are tokenized via HLQ, becoming now new token types. So we extracted here a dynamic in these video frames, and now we say, okay, now we have a flow token or a depth token or a segment token as discrete maps that we can now have a higher value object if you want, and now we can understand here the content of this video frame because now we have a higher complexity structure in our objects built. And of course, we feed those objects back as new token types, and we calculate with these new token types. So this step is here, if you want, like a detective finding here new patterns. Poking here the scene reveals these aha insight moments, like tracing here some footprints, like the flow to group suspect segments, and so on. So a self-learning autonomous system just needs to watch, I don't know, 10,000 videos of bouncing balls to understand what is happening. So this was structure extraction. And as I already told you, and now we have those defined, and now we integrate these structures as new objects, as new elements here, as new vocabulary that we can use here in the training cycle here. And then we close the loop, and this is a self-learning system. Great. So let's look here at the third part, closing the loop, integrating now the structure for the self-improvement of our AI systems. They are not just outputs, they are also integrated back, creating here beautiful circles, and you understand immediately what we are talking about. New structure tokens, I showed you the flow token, the depth token, segmentation token. We put them back into the mixed sequences with our RGB tokens. And since we are now again in a beautiful sequence, we can resume here autoregressive training with our normal GPT or Gemini systems here to refine now size joint distribution. The system will learn, become better and better every turn. The mechanism is, again, tokenize the structure, flow map, create here mixed sequences, interleaved here with RGB and pointers and values and flow and whatever, and resume autoregressive training with the old data, new data. And the beauty is we have no architecture change. We don't have to build new architectures, new transformer layers, new transformer heads, no complexity added to the architectural structure. The new tokens have a dual role, conditioning and targets at the same time. So input to the control, specify the flow to edit motions and also to predict them from an RGB. Expands the PGM joint distribution framework. Great benefit, you have better control. You can nudge object via the segments, you can steer the views via the depth algorithm. You have improved extraction, you have a bootstrapping if you want. You can unlock new tokens, higher complexity objects in your video stream. You have three-dimensional meshes here if you combine depth and flow information. So you have here a beautiful tool set how you can optimize here the learning process of this vision AI further. Predictor upgrade, yes, of course. They give you 3 examples. I just mentioned one. The physical video editing, you are familiar with currently with this Nano Banana from Google. Imagine this is now working directly in video. This is the next step. Conditions here on segments, on flow for realistic edits here in video. So you say, hey, in this video, hey, now add a camel and the camel should walk here in the background. Or you update the shadows of particular objects, or you delete shadows, or you create new scenes here. Physical video editing. Great. Let's look back, take a step back, look at the complete cycle. Psi complexity is not simple. Don't underestimate it. It's a scalable PGM via a particular methodology. We have causal prompting for structures and token mixing for the bootstrapping here, for the self-learning. And it challenges all the traditional AI systems we have up until now by unifying here the generative discriminative task into one model, which is beautiful, emphasizing here the distributional causality over the point estimates. However, this needs a lot of training resources. Imagine all the, let's say, YouTube videos that you have to watch, that the AI really understand what are all the objects in the world. What are all the people looking like in the world? What are all the cars looking in the world? What are all the buildings in the world? What are all the boats in the world? How do they move? What is their impact resistance? What can you burn? You get the idea. Summary. Yes, beautiful. Let's come to the summary. What is the beauty? A vision-only world model. You have no intelligence that comes in from the linguistic part, from the large language model part. You have an intelligence in vision. Yes, Psi, trained exclusively on raw video data streams. Beautiful. No linguistic elements. You have no reasoning chain that swap over from the linguistic model. Everything is visual. How beautiful is this? Also then, of course, for robotic application. This model, nature doesn't know what language you speak. You just see the ball bouncing here on a surface. Yeah? So all the laws of nature, the physical regularities, motion, depth, object coherence, and everything that you record with your video frame, all of this is now, if you want, to training data set so that the AI understands the laws of nature, physics. And this is only through probabilistic prediction over those patches, 16 times 16 pixel, whatever you choose, without translating here the visual content into any linguistic representation or relying on any chain of thought linguistic thinking. Vision only. Isn't this beautiful? It's the real beauty, the departure from the language model paradigm. You have the intelligence in the language model, you have the reasoning in the language model, you have the causal argumentation in the language model. No, forget about it. We have, from the ground up, a vision model that learns here only watching videos here, enabling here direct non-linguistic controllability in the visual domains. Isn't this beautiful? Have a look at the paper. It is gorgeous. It is not easy. It is not trivial. You will spend quite a lot of time. Prepare about double the time that you normally need to read a paper. But I can tell you it's worth reading the paper. Have a look at it. There's so many additional numerical information and additional data available for you in the print by Stanford University. Subscribe and I see you in my next video.